So a short summary of this week is that if you have some material, put it in an electric field, it becomes polarized. So we define this polarization. And polarization basically corresponds to the displaced charges or rotated charges. And due to this displacement or polarization, there is induced charges in our system. And due to this induced charges, which we call them which we can write in terms of the given polarization vector, the electric field will be modified. And instead of working with the electric field, we define what this quantity called the displacement field, because the advantage of defining the displacement field is that it is directly related with the free charges that we are in control. In a sense, at least if you look at our equation, the divergence of the displacement field is equal to rho free. It doesn't make any reference to the material. So it's just as if material doesn't exist for the displacement field. We will see that this is actually not the case, but it just looks as if the material doesn't exist. Now, one problem, though, is that, eventually we would like to be able to calculate these fields, and to be able to calculate a vector field, we need to know the divergence of that vector field and also the curl of that vector field. Although we know the divergence of the displacement field, we know the curl of the electric field. So somehow we need to relate the two if we want to be able to solve for the electric field and hence the displacement field. Well, there's a relation between the displacement field and the electric field, the first line, but that is also not so useful because in that equation we don't know what the polarization is. Now, these things we will be discussing next week. So how to calculate the displacement field for a given system, how to relate the displacement field and the electric field. So for this week, let's just let's look at an example first. Now, you see, most of the time we don't refer to this one, especially when we were talking about the Gauss law and taking Gauss surfaces, etc. We never worried about the curl of the electric field. We never even mentioned it. So it was as if that equation was not necessary. But that is not the case, because if you remember, Gauss law we can use for very symmetrical systems. And in those symmetrical systems, it is the symmetry that kind of makes sure that the curl of the electric field is zero. Well, we can basically do the same thing for the displacement field. Let's say that we have this wire carrying some surface charge density, let's say called sigma on the surface. It has a thickness dA to radius. It is covered, if you look at this wire, there is some conductor inside with a finite radius. Outside is covered with a plastic. Outside we have a cylinder. This is made up of a dielectric. So the question is, what is the D field? Everywhere. Now, we know that the D field satisfies this equation, from which if you just integrate this over a volume, it tells you that the integral of the D field over any closed surface is actually equal to enclosed free charge. So this is what we can use in this system. So how would you propose that we should proceed? So how can we use that integral equation to solve for the displacement field? Okay, we can just imagine any Gauss surface. In fact, inside or outside doesn't really make any difference. Well, we know that this displacement field will be in the, let's say, S hat direction, S being x squared plus y squared. This is z, this is x, this is y. And d depends on s only, the magnitude. It will be radially out. This is what this s vector, s hat vector is. It's a unit vector away from our wire and perpendicular to the wire. Now we can separate this integral into three parts. Well, this is our Gauss surface, the dashed line. It is outside the inner conductor, but it can be inside the dielectric or outside the dielectric. We don't even need to know that. Now this will be the integral of d dot ds over the top, of d dot ds over the bottom, and the integral of d dot ds over the side of my cylinder. Well, you see, at the top and the bottom, by top and bottom I mean the top and the bottom, you see ds is pointing on the surface, ds will be pointing in this direction. And displacement field, since it's in the rho hat direction, it's pointing in this, somewhere in this direction. They are perpendicular to each other. So this is 0. The same thing holds for the other side, because in that case, rho displacement field is still in this direction, somewhere in this direction, but the surface element is in this direction. So they are perpendicular to each other. Their scalar product is 0. The only contribution will be from the sides. And on the sides, ds is nothing but its magnitude in the s hat direction. So that basically tells me that d dot ds on the sides is just the product of the components. But on the side, this is just a constant because S is constant on the side of our cylinder. I can take it out. And the total, what remains is the total area of the side of my cylinder. Let's say this, oops, sorry. This side is, the radius is small s, and the height is h. So this is 2 pi small s times h. This is our d dot, the integral of the displacement field over our Gauss surface. What is enclosed free charge? Inside this Gauss surface? Ps squared times h. That is the volume inside our Ps squared or Pa squared? Pa squared. H, this is the volume inside my cylinder. And the, 2Pa. I have a surface charge density, not a volume charge density. So the surface of the wire inside my cylinder is just 2 pi A times H, and the charge per unit volume is sigma. So this should be equal to 2 pi A times H sigma. Well, if we make the cancellations, 2 pi's cancel, D on the side, H cancel, it's just A over S times sigma. Or I can also write this as 2 pi A sigma over 2 pi S. Now, the reason why I wrote it like this is 2 pi a times sigma is nothing but the charge per unit length of the wire. So this is charge per unit length. And hence, I know my displacement field is equal to 2 pi a times sigma over 2 pi s in the s hat direction. Now we can determine, in this example at least, we could determine what the displacement field is. Now, of course, it will be interesting to obtain the electric field also. But remember, the electric field is related with this displacement field through this relation. Okay, another thing to note is we obtain the displacement field, well, we just behaved as if the dielectric is not there. Because in the expression of the displacement field, the electric properties doesn't appear. So this is the displacement field inside my dielectric. This is the displacement field. This is the expression of the displacement field outside my dielectric. It doesn't make any difference for the displacement field. But it will make a difference for the electric field. You see, if we are looking for the electric field outside the dielectric, what is the polarization outside the dielectric? Remember, polarization is the dipole moment per unit volume. What is the polarization outside our dielectric? So I have this, my wire. So at this point, for example, what is the polarization? Well, the definition was the dipole moment divided by the volume. So what is the dipole moment here? Remember, this is empty space. 0. Nothing can create a dipole moment. There are no charges over there. So the polarization outside the dielectric is 0. So outside the dielectric, the electric field is nothing but the displacement field over epsilon 0, which is 1 over 2 pi epsilon 0 s in the s hat direction multiplied by 2 pi a sigma. It is just a vacuum result. I mean, the dielectric over there around our wire doesn't really influence the electric field outside the wire. Yeah, that is kind of expected because the dielectric has this cylindrical shape. There will be some charge density induced, but it will behave as if it is. It will also be cylindrically symmetric. So for an outside observer, all the charge of this dielectric will behave as an infinite wire at the center of this dielectric. What is the total charge of the dielectric? 0. So it won't have any effect outside. This is what we had seen over here. Inside the dielectric is another story. Because the electric field inside the dielectric will be d over epsilon 0 minus p. What is p inside the dielectric? We don't know. We should first calculate it. And then we can determine what the electric field is. But for the time being, we cannot determine it. So we don't know what the... Now, P over epsilon 0. We don't know what the electric field inside the dielectric is. Now let's repeat this exercise for a sphere.
Hocam question?
Sure.
In previous example, why they integral of ds in top and bottom is zero? What is perpendicular?
So you see, what we are evaluating is the integral of E dot ds, no D dot ds. Okay, and we are integrating this over the surface of this cylinder. Well, the cylinder I divided into three parts. This flat part over here, the flat part over here, which I call the top and the bottom, and the side of the cylinder. If you look at these flat parts, what is the this flat part, for example, what is the direction of ds? That is ds. What is the direction of the displacement field? This one. What's their scalar product? Zero. E dot ds is zero at every point on this flat part. So their integral is zero. Similarly, for this flat part, d dot ds is zero. So its integral is zero at every point on this flat piece. So that is why d dot ds is zero on the top and the bottom.
And why did we multiply d by 2 pi and divide it by 2 pi?
You mean here?
Yes.
What is 2 by a sigma?
This is the charge and this.
Well, you see, we found that this is the enclosed, Q enclosed free. Let me just take it. This is the charge in a length h of wire. What is the linear charge density? That is one parameter which we quite often use. Linear charge density, which quite often we use the symbol lambda to denote the linear charge density. This is Q divided by h, which is 2 pi a times sigma. So actually this expression over here is 1 over 2 pi epsilon 0 s times lambda in the s direction. Now, before when we studied the electric field of an infinite straight wire with linear charge density lambda, this is the expression we obtained. So that's why I multiplied and divided by these 2 pi a.
Hocam bu soruda niye displacement var? Yani nasıl bir displacement var?
Displacement.
Hani elektronlar mı hareket ediyor, elektrik alanına mı koydu?
Why do we call this the displacement field? Or is that the question? Yeah. Here we have a dielectric. You take this wire. This wire has inside there is a conducting core. Outside there is a dielectric insulator, insulating cylindrical shell. Well, this carries a current, but what we assumed here is, let's just assume that we put some net charge on this conductor inside this wire. Well, there is a net charge there. The dielectric is an insulator, but nevertheless the charges will be slightly displaced if there is an electric field. But there is an electric field because we put some charges in the conducting part, which creates an electric field, which displaces the charges in the insulating cylindrical shell. So we have a displacement of charges. And hence it is polarized. Not really. I mean, of course, when you first start putting the charge on the conductor, the charge will be moving around. You will be creating displacement in time, but then you stop putting any more charges. The total amount of charge is fixed. The electric field it creates will be fixed in time. The displacement will be fixed in time. The polarization will be fixed in time. So nothing will change with time. So that is electrostatics. Well, of course, soon we will be going away from electrostatics. We will look at magnetostatics, which involves moving charges. But still, we are in electrostatics.
Hocam, in this question, why did we find lambda? How is it used before?
Well, what would you like to use to describe your problem? Do you prefer sigma? Well, use sigma. Do you prefer lambda? Use lambda. Do you prefer something else? Use that one. Whichever one you prefer. I mean, lambda is nicer mainly because it has a resemblance to our previous results of an infinite wire. That's why I switched to lambda rather than sigma. Just to make the resemblance more apparent.
Hocam, yüzey olarak almamızın büyük sebebi kondaktör olması değil mi? Başka bir sebebi mi?
Well, here, if you cut it, you will see that it has a thickness. And hence it has a surface.
Hacim anladık ki.
Well, it's a conductor, and hence the charge will move to the surface. It will not stay in the volume in electrostatics. In a conductor, the charge is always on the surface. But of course, you can also write it as a volume charge density using direct deltas if you want. It's up to you, whichever one you prefer. Other questions? So we have an inner conducting sphere which has a volume charge density rho, or let's say non-conducting, since it's a volume charge density. If it was a conductor, all the charge will move to the surface. So let's just assume we have a sphere that has a uniform volume charge density rho. It is surrounded by a dielectric. Another dielectric, let's say. They can even be made from the same material. So what is the displacement field? Well, the idea is basically the same. First of all, the displacement field, the problem is quite symmetric. Since the problem is quite symmetric, the displacement field has to be radial. It has to have this form, because nothing changes if you rotate our system around the center. So d dot ds, if we integrate it around any spherical surface, will be just dr. The surface element is just r. Let's say the radius is r. dr r squared ds, because ds, ds is also radial. So d dot ds is nothing but the product of the radial components. So this integral will be, well, over the surface, dr is just a constant. What remains is the integral of the surface over this closed surface. And the total surface area is just 4 pi r squared. And at the same time, this has to be equal to 4 over 3 pi r cubed rho. Since I'm outside that region, which contains the charge density, the charge density, well, since it's uniform, I multiply it with the volume. Let's say this is R0. R0 is the radius of the region that contains the charge. And hence d of r, the displacement field at a distance r from the center, is just 1 over 4 pi r squared times q tot, the total charge. And hence the displacement field at the point r, let's say this is 1 over 4 pi r squared times q tot, total charge in the r hat direction, if r is larger than r0. And we are done. This is the displacement field. Again, it doesn't help that much because what we are actually interested in most of the time is the electric field. We don't really know the relation between the electric field and the displacement field yet. But if we are outside the dielectric, the electric field, since the polarization is 0, because outside the dielectric there are no charges to polarize, there's no material, so the electric field is just the displacement field over epsilon 0, which is 1 over 4 pi epsilon 0 q over r squared in the r hat direction. Now this is again our well-known result for a uniformly charged spherical object. We are observing it from outside. Now here we didn't really need to know what the curl of D is. It is automatically 0 because of the symmetry. So just the last warning on this issue. We had seen that the divergence of E was equal to rho over epsilon 0, and we could solve this equation basically by stating that the electric field was equal to 1 over 4 pi epsilon 0, electric field at the point r, integral of rho of r prime times r minus r prime divided by r minus r prime cube, d cubed r prime. Now we know that the divergence of the displacement field is equal to rho free, but the displacement field at the point r, well, these two equations basically are identical. The only difference is that here we have rho over epsilon 0, here we have rho free. Just make the replacement. R minus r prime divided by r minus r prime cube, but the displacement field is not equal to this one in general. Because the thing is, this is not the solution of this equation only. That is the solution of the divergence of E is equal to rho over epsilon 0 and curl of E is equal to 0. So these two equations, with the boundary condition that E goes to 0 at infinity, it gives you this solution. But if you have this condition, since we don't have, in general, curl of D is not equal to 0 in general, D cannot be written in this form. Because whatever you can write in this form, it has 0 curl. So if the curl of the displacement field is non-zero, then you cannot write it in that way. Of course, nevertheless, for symmetrical systems like these ones, we can determine the value of D. And later on, we will see that for a general material, we will see how to evaluate D and the electric field.
Yer değiştirme rotasyonel olabilir anlamına mı geliyor bu? Displacement rotasyonel olabilir anlamına mı geliyor?
You see, displacement is just displacement. It's not rotational, it's not linear, etc. It's just displacement. One object was here, and then it was here. In this case, the name basically derives from the fact that the charges are being displaced. They can go from here to here or here to here. I don't really care. They are displaced. Displacement field is basically a kind of electric field in a sense. It is in vacuum, it is the electric field. Now let's look at some boundary conditions. Now, here the boundary condition that we will be interested in is basically, in real life, what are the problems that we are interested in? Let's look at the window. There is the light or the electric field. Let's say it has to kind of propagate in atmosphere and also the glass. So there are different materials. And somehow we have to know the potential at each one of the materials and how the potential changes across materials. So that is the kind of boundary conditions we will be interested in. So we have two different materials. They will be separated by such an interface. So how does the electric field and the displacement field changes? We had already done this in the case of the electric field, but let's just also review that one. Now, the electric and displacement fields, they both satisfy these conditions. They satisfy these conditions. Curl of the electric field, whether you are in matter or not in vacuum, it doesn't matter. Curl of the electric field is always zero. Whether it's the microscopic electric field or the average electric field, it also doesn't matter. Curl of the electric field is always zero. And the divergence of the displacement field is equal to rho free. Now, if you look at the curl of the electric field and integrate it over some area, any area, just imagine any area, integrate the curl of the electric field over that area, it is also zero because curl is zero. But that basically tells us that we know that the curl of a vector field integrated over an area, we can always write it as the integral over the boundary of the area of the vector field itself. The boundary of the area is a closed loop. So this should always be satisfied, whether you are at a boundary or not. It doesn't make any difference. It should always be satisfied. Now let's come here. Let's imagine a very small rectangular loop such that the two opposing sides are on each side of this loop, on each side of this interface. And let's say you are going around that loop in that sense. Let me give some names, A, B, C, and D, to all those points. Let me also define the inside and outside. It doesn't really make any difference which surface you call the inside, which surface you call outside, just to give it some names. And the electric field might have different expressions inside or outside the surface. Now, E dot dl around that closed loop will be from A to B, E dot dl, from B to C, E dot dl, from C to D, E dot dl, and from D to A, E dot dl, and this should be zero. Since it should be zero for any closed loop, I just choose a particular one, and the integral of the electric field around that one should be zero. Now let's look at the integrals from B to C and from D to A. Well, I will be assuming that, you see, the important thing is that AB segment and the CD segment should be on both sides of my surface. Keeping the AB and CD on both sides of the surface, I can shrink the other side. I can take that value to zero. Well, if I take that value to zero, you see AB is on one side and CD is on the other side, This electric field is finite. I'm integrating a finite number over an interval that shrinks to 0. So this value and this value goes to 0, these two integrals. Let me give some names. Let me call this length L and this length K. So this one and this one, they both go to 0 as K goes to 0. Because as K goes to 0, both sides can still stay on the different sides of my surface. That is why I can easily set K to 0, K to 0. Now let's look at the other integrals. E dot del from A to B and from C to D. As I go from A to B, I go in this direction. As I go from C to D, I go in the opposite direction. So dl vectors, as I go from A to B, and the dl vector as I go from C to D, they are in opposite directions. And again, the L, total length L is very small. It will be very small, non-zero, but very small. Within this length, the electric field will not change. So electric field will be almost constant. I can just take it out of this integral as I go from A to B. This will be constant. Take it out. What remains is the total vector. Let me call that vector L. This vector is my L vector. So 0 is equal to E inside minus E inside times L. This is the integral from A to B, plus E outside dot minus L. This is the integral from C to D, because as I go from C to D, I'm going in the opposite direction, in the minus L direction. L is parallel to my surface. Remember this, I already set K to 0. So I have this very thin loop. The two sides should be parallel to the surface so that they both stay in the different sides of my surface. So when I take this scalar product with L, what I actually obtain is just the horizontal component. So divide by L, both sides. So 0 is equal to E inside minus E outside dot L hat. Well, this I can also write it as E inside, the parallel component parallel to the surface, minus E outside. Again, the parallel component is equal to 0. So the electric field, whether we have a material or not, if we have a surface, it can be an actual surface or an imaginary surface. It doesn't matter. If you imagine any kind of surface, the parallel component of the electric field parallel to that surface should be continuous. Its value on one side of the surface should be equal to its value on the other side of the surface. This is always true. Now let's look at this is the consequence of the equation that the curl of E is always equal to 0. Whenever you have a vector field whose curl is always 0, you can always say that its component parallel to a given surface will be continuous across the surface. Now let's come to the other equation. We know that the curl of E is equal to 0. We know that the divergence of D is equal to rho free. And the divergence, you see, by Gauss law, we just evaluated over a volume. We convert it into a surface integral. So we know that D integrated over a closed surface is the total enclosed free charge. Not the charge density created by the displacement of charges, but the charge that we put over there on that surface. So to see the consequence of the divergence of D is equal to rho free, we first have to choose some imaginary surface, closed surface, and we can take this closed surface to be kind of a cylinder. with height, let's say, h, and the surface area A. I will basically do the same trick for this cylinder. In this case, I just sent the side to 0 so that the other two sides were on both sides of the surface. In this case, I will set this h to 0 so that the top and the bottom of the cylinder will still stay on the two sides of my surface. Now this d dot ds will be equal to the integral of d dot ds over the top plus the integral of d dot ds over the bottom plus d dot ds over the side. Now I can set h to 0. I can take the limit as h goes to 0. But as h goes to 0, let's look at this one. I'm integrating a function over an area. Well, this function over our area is almost constant because our area is within a very small region. In that region, our function doesn't really change much. So this is a constant. I can take it out. What remains is the total side area. But as I take the limit h goes to 0, the total side area goes to 0. So this integral is 0 in that limit. So this goes to 0 as h goes to 0. Now let me define this vector n. I will need that. N is a unit vector perpendicular to the surface. So at every point you get a different n. And it is pointing from inside to outside. So at the top region, this is our top. ds is nothing but a in the n direction, or let's say dA. This is our bottom. At the bottom, ds is equal to, again, dA in the minus n direction. You see, I have this cylinder. N vector should be, this top and the bottom are parallel to the surface, but n vector is perpendicular to our surface, so this n vector is perpendicular to the top area and the bottom area. And ds vector is a vector that is perpendicular to my area. So the ds vector is either in the direction of n, at the top it is in the direction of n, at the bottom it is in the direction of minus n. So this is equal to the outside dot n ds. Remember, this is, we are evaluating at the top plate, plus the inside dot n ds bottom. Well, I call these A in the above expression. Well, my areas are very small. Since my areas are very small, these are almost constant within that area. I can just take these and this one out. What remains is just the outside minus the inside scalar product with n times A. This should be equal to total free enclosed charge. Well, if there are free charges on the surface, this is the total free enclosed charge in my cylinder. Now I can cancel the A's. So although the component of the electric field parallel to our surface is continuous, the component of the displacement field in the direction of n that is perpendicular to the surface is not continuous. And it is not continuous if we have some free charges on this interface. Well, for most practical applications like this window and the atmosphere, there are no free charges over there. We didn't put any charges over there. So sigma free is 0. So the perpendicular component of the displacement field will also be continuous. Parallel component of the electric field will be continuous. The perpendicular component of the displacement field will be continuous. But the electric field will not be continuous still. Because since the atmosphere and the glass have different polarizabilities, they will have different polarizations. You see, this displacement field is continuous, but the electric field is displacement field minus the polarization. Polarization is discontinuous, so electric field will be discontinuous. But the displacement field will be continuous. Okay, now we are just having all these bunch of fields. We have the electric field, the perpendicular component, the parallel components, etc. And now we have this displacement field. They are related, but they are different quantities. Now, any questions? You see, I'm taking a scalar product with a unit vector. The scalar product with a unit vector gives me the component of that vector in the direction of the unit vector. N is perpendicular to the surface. So when I take the scalar product with n, I obtain the component of this expression perpendicular to the surface. Now later on, what we will be studying are systems. For example, we will have some charge in one dielectric and nothing on the other dielectric. We will have this interface. So how does the electric field change across this dielectric? To study that, we will be needing these expressions, the discontinuity of the displacement field and also the continuity of the parallel component of the electric field to be able to relate the electric field in both dielectrics and hence obtain the solution for the electric field. Any last minute questions? So see you next week. Have a nice weekend.